Bismillahirrahmanirrahim. Hello students, welcome to the Electrical Engineering channel. In this lecture, we will move forward and take our discussion to potential difference. In the previous lecture, I demonstrated the concept of work and energy in electrostatic fields. So the potential difference can be defined as work done in moving a unit positive charge in the electric field, and in case of work, we had the mathematical expression of W equal to minus Q integral from initial to the final position E dot dl. And potential difference is the same expression as that of work, but in case of potential difference, the charge considered to be moved in the electrostatic field is a unit charge. So potential difference is basically defined as the work done per unit charge, right? So work done per unit charge is called potential difference. So mathematically, potential difference is equal to minus E dot dl integral from initial to the final position, and VAB is equal to minus integral from B to A E dot dl. So the units are volts, and potential difference between points A and B can be defined as the amount of work done in moving a unit charge from point B to A in the electrostatic field or electric field. So this is VAB, and for a line charge, we have the expression of W equal to Q rho L over 2 by epsilon L and B over A. This is the same expression that we derived over here. And VAB is equal to W over Q, so it will be equal to rho L over 2 by epsilon L and B over A. And for a point charge, E is equal to Q over 4 pi epsilon R square AR. This is the expression of work and potential difference for a line charge, and for a point charge, this is the expression for electric field, and dl is equal to drar. So VAB can be calculated by evaluating this line integral, and it will be from RB to RA Q over 4 pi epsilon R square dr. So upon solving this integral, we will get Q over 4 pi epsilon 1 over RA minus 1 over RB. If RB is greater than RA, then VAB will be equal to positive, and VAB is the amount of work done in moving a unit positive charge from point B to point A, and VAB is equal to VA minus VB. So Q over 4 pi epsilon RA is equal to VA minus Q over 4 pi epsilon RB is actually equal to VB. So both are written over here, and if point B lies at infinity, VB is equal to 0. So if we assume that this point B lies at infinity, then RB will be equal to infinity and VB will be equal to 0. And in that case, VAB will be equal to VA, and VA is called absolute potential at point A. And absolute potential at point A can be defined as the amount of work done in moving a unit positive charge from infinity to point A. So this is called absolute potential at point A. So potential difference and absolute potential both are different quantities, and both are defined over here. And one more thing that I want to inform is that work done is equal to minus Q initial to final position E dot dl. So whenever we solve this integral to solve any example or a numerical problem, we will uh, come to know that work done on a charge will always be equal to positive, and if the work is done by the charge, the final expression will be evaluated as negative. So if the final answer of work is evaluated as positive, it means the work is done on the charge, and if the final answer of work is evaluated as negative, it means work is done by the charge. So the difference between work done on the charge and work done by the charge is that if we are exerting a force on a charge to move it in the electrostatic field, it means we are doing work on the charge, and if the charge is automatically moving in any direction against the external force, then it means work is done by the charge. So technically, that work should be positive, and if the work is done on the charge, that will be positive. So now I will solve a simple example to have a deeper insight into the concept of work. So if we are given a charge of 4 coulomb and we have to move this charge from point B to point A, the coordinates are given. We have to calculate the total amount of work done. So let's solve this problem. dl is equal to dx plus dy plus dz and we have to follow this path. Y is equal to 2 minus 2x and z is equal to 5 and electric field is given as 5ax. So work is equal to minus q e dot dl and q is equal to 4, e is equal to 5ax dot this is dl. So it will be ax dot ax. Rest of the dot products will be equal to 0 and it will be minus 20 dx and the final answer will be equal to 20 joule after putting these limits. In the second part, the electric field is given as 5x ax. So again, this will be very simple integration and work will be equal to minus 20 x dx and the final answer will be equal to 10 joules. In the third part, electric field is given as 5x ax plus 5y ay. Again, we can evaluate this line integral and after evaluating this integration, the final answer is calculated as minus 30 joule. So here we have got a negative answer. It means work has been done by the charge, and in these two cases, the work is done on the charge. So let's solve another example, and in this example, we are given a point charge of 15 nanocoulomb placed at origin, and we have to calculate the absolute potential at point P1, and we are given that the potential is equal to 0 at this point. So for a point charge, electric field is given as Q over 4 pi epsilon R square AR, and this is equal to dl. So E dot dl will be equal to minus Q over 4 pi epsilon R square dr. Rest of the dot products will be equal to 0, and this will be equal to Q over 4 pi epsilon R plus constant of integration. So this constant of integration will be evaluated by using this condition that V is equal to 0 at this point. So let's put this condition. V is equal to 0 and it is equal to q over 4 pi epsilon. This is r and this is c. And r is equal to 6 square plus 5 square plus 4 square under root plus c. Because the source is actually placed at the origin. So actually it was r minus r dash, but r dash is equal to 0. So we just have r over here. And all of the quantities are known. So c can be evaluated to be minus 15.38. Now we will put this value of C in this original expression to calculate V at the given point. So V will be equal to 135 into 1 by 14 under root minus this value is equal to 20.7. So this value has been substituted in this expression. R is also evaluated uh, for this point, right? Minus 2, 3, minus 1. So minus 2, 3, minus 1. So R will be equal to 2 square plus 3 square plus 1 square. So 2 square is equal to 4 plus 9 plus 1. So it is actually 14 under root. And this is the other expression. And the absolute potential is evaluated as 20.7 volts. In the second part, we are given V equal to 0 at infinity. So we will use this condition in this expression. So 0 is equal to q over 4 by epsilon. This is infinity plus c. So c will be equal to 0 in this case. And V is equal to 135 divided by 14 under root, and this is equal to 0, so it is 36.08 volts. In the final part, the condition is given as V is equal to 5 volts at this point. So from again equation 1, we will use 5 volts over here and we will use coordinates of that point over here. So 5 is equal to 135 over 20 under root plus C, so C is equal to minus 25.2 volts and V will be equal to 135 by 14 under root minus 25.2, so it is 10.88 volts. So now we will discuss the case of a ring of charge. So suppose this is a ring of charge and it is placed at z is equal to 0 plane, and we have to evaluate the potential at this point whose coordinates are 0, 0, z. And again we will have to use the line integral formulations. So dl will be equal to a d phi in this case because the ring of charge is actually located along the phi direction. So this is the differential patch or differential element, and the length of this differential element is equal to a d phi. A is the radius of this ring, and dq is equal to rho l dl. So this is rho l, and dl is equal to a d phi, and r is the location of this differential element. R dash is the location of the point where we want to measure the potential. So R dash is equal to ZAZ, and R is equal to A phi. So V will be equal to Q over 4 pi epsilon R minus R dash magnitude, and dV, differential amount of potential, will be equal to rho L A d phi divided by 4 pi epsilon A square plus Z square under root. And we have to evaluate the integral, line integral of this expression to calculate the total potential. And V is equal to integral from 0 to 2 pi, because we have phi over here. So it will be equal to rho LA over 4 pi epsilon into this expression multiplied by 2 pi. So the integration of this expression will be equal to, here we have d phi as well. So the integral of d phi is phi, and when we put these limits, we will get 2 pi over here. So it will be cancelled out with this 4 pi. So we will have 2 epsilon over here. And this is the expression of the potential at this point due to ring of charge. And again, another thing is that the closed integral of E dot dl is always equal to 0. It means that what work done is in moving a charge along the closed path is 0. So E is also a conservative field. So work done in moving a charge in a closed path in the presence of electric field is always equal to 0, and this is the definition of a conservative field. So just like a gravitational field, which is also a conservative field, electric field is also a conservative field. So all static electric fields are the examples of a conservative field. But a time varying electrostatic field or time varying electric field is not a conservative field, and we will discuss this feature in the coming lectures when we discuss the electrodynamics. Another thing is that the sum of voltages in a closed circuit is always equal to 0. So this is also the demonstration of this expression of E dot dl along a closed path is equal to 0. And both expressions are actually telling the same concept. So that is all about our today's lecture on potential. I hope you have understood the concepts discussed in this lecture. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.